Okay, so here what I'm going to do is I'm going to go through a quick introductory video on how to use the RL tool. And so this is a built-in tool in MATLAB that allows you to manipulate the root locus as well as seeing the response of the system, various responses of the system. So the way we're going to do this is I'm going to declare my S variable, just the TF of S, just to create our S, and then I'm going to I'm going to call this RL tool with a plant transfer function and a controller transfer function. So this is the one that we're going to be using in the example, the next example. So this is the open loop plant, and then we're just using proportional control, and so I'm just giving it a transfer function of 1. So this is true with all of the tools that MATLAB is going to use. Starting with the RL tool, that gain K is something that we're going to choose, and so we don't explicitly put that into our call of the RL tool. So once we hit enter, that's going to open up a window that essentially looks like this when you first open it. And so the first thing I like to do is I like to go ahead and get rid of this upper toolbar so I can see a little bit more of stuff. This left-hand browser window here isn't particularly useful, so I go ahead and minimize that. And then just like in MATLAB, you can drag and drop these plots around. So I can move this over to one side, and this is how I like to use this. And so what this is showing me is on the left-hand side, it's the root locus. And on the right-hand side, it is the step response. And in particular, it's the step from the reference R to the output Y. And so that's why it's saying R to Y. And it's a response to a step response, which is oftentimes what we'll be interested in analyzing, because that's how we look at our time domain specifications. And so these, so for a nominal, whatever value our K value is currently, that locates our closed loop poles at these purple dots. So in this case, we have 2 open loop poles, which means we have 2 branches of the root locus. And so it means that at every value of K, we're going to have 2 closed loop poles. And so that K is equal to 0, these closed loop poles are going to be at these open loop poles. And as we increase them, they're going to move along the real axis until they hit this merging point, and then they're going to branch off. And so that's hopefully at this point in time, you can go ahead and sketch this by hand. And so what we're going to do is, the cool thing about this RL tool and having the step response right here is the fact that we can go ahead and slide, we can grab, see how the tool changes, the mouse changes, we can grab these purple dots and move them along the root locus and observe how the step response changes. So just to make that super clear, I'm going to show you a couple of things that we can do with the RL tool. So one of them is I'm going to right click on the root locus, and there's a couple of things that I can do. Here, what I can do is I can select Edit Compensator, and that pops up this window that essentially shows me what my controller looks like right now. And so right now it's saying that it simply just has a gain of 1. And in this case, there's no dynamics. In the future, if we wanted to, for example, change this to be a PD controller, I could right click and I could add a, for example, real 0, and that would give me the option of adding a single 0, which would correspond to a PD controller, for example. If I wanted to add some of our more sophisticated controllers we'll get to later, I can go down here and we can construct just about anything. We can add a 1 over S term like this, and so that's going to ultimately change the root locus. And that's part of the reason why we need to know how to sketch the root locus, so we can anticipate the kinds of changes we would observe in the root locus if we added different terms. All right, so it's useful just to observe what this does. So if I change this to 0.8 and I hit enter, what you're going to notice is that the purple dots have moved, and so those have shifted down. And so that has also made a change in our step response here. Likewise, if I were to move this out of the way and I can take this and slide this along, you can see that the closed loop poles are moving along the root locus, and the step response is changing accordingly. And so at this point in time, I've kind of moved them back to where they were before. So let me go ahead and move these down here. And at this point in time, I'll bring the compensator window back in, and it's about 0.33. And so that just tells you what your current proportional gain is going to be. So there's a couple of things that we can do to make our lives a little bit easier. And that is that MATLAB has built in some tools to visualize and help quantify these time domain specs. So if I come over here to my step response, I can right click here and I can select characteristics, and I can select, for example, the rise time. And so what that's going to do is that's going to give me a little dot that I can either hover over if I want to just see it, or I can click on, and then it actually keeps this window open. The other convenient thing you can do is you can grab this and move it around so that you can keep seeing multiple of these at the same time. So what it's telling me right now is that my rise time is 1.77. If I were to also add in my peak response, then I can click on that, and now you can see how it's useful to be able to kind of move these things around so they don't overlap too much. So this is our peak response, and so now it's telling me that I have an overshoot of 14.5, and the peak time is 3.87. So likewise, you can manipulate and select these other different characteristics by adding them, by selecting them here. Just so it doesn't get too busy, I'm gonna keep these two up. And then what's cool is I can essentially take this and I can drag this around, and you can see that in real time we're going to update what the overshoot is and what the rise time is. And so this is going to help me achieve my my time domain specifications that I'd like to accomplish. So this is actually telling you the real values of what this is. So these are numbers that you can directly trust. In this case, we're dealing with a second order system, and so in that case, our time domain specification geometries are going to be exact, because those essentially assume that we have a transfer function that has no zeros and has two complex poles. So once we move on to systems that have zeros or have additional poles, this is not going to be completely accurate, the geometries that we talked about before, but there's still a very useful guideline for how to manipulate systems. So in this case, one thing that we can do is we can select design requirements, and we can select in here, let's just go ahead and select that we want our natural frequency to be at least, say, 1.8 radians per second. And so if we do that, what that's going to do is that's going to create that semicircle that we talked about based on that criterion. And so now this gives you a nice visual that says, okay, my poles need to be outside this region for me to be able to achieve the time domain specification. And again, these geometries are going to be based on second order systems without any zeros. And so that's going to be accurate pretty accurate for this system. But as we add more poles or more zeros, this is merely going to be an approximation. So it could be the situation that you pull your poles into this feasible region, and then you come over and take a look at your time domain specifications, and they don't actually achieve your goals. And so that's merely because the transfer function that you actually are dealing with is something more complicated than that simple second order system that we assumed when we came up with these different geometries. And so likewise, again, we don't have any time domain specification to talk about right now, but we can just kind of make up some numbers. And so I could talk about a damping ratio of some value. And so that would create this cone, again, that we talked about. And this would help you to identify, again, if you trusted these regions to be accurate, if this was a pure second order system, this would clearly show that there's no way for you to achieve your time domain specifications. Because there's no place where the root locus goes that actually gets you to this nice region, this feasible region out over here. And so this is the way that we're going to be manipulating the different examples using the RL tool. Again, if we wanted to, we could right click in the white area here, and we could go back to our edit compensator. And in this case, just to kind of show you what it looks like, we can go ahead and add a real zero. And so the way that looks like is we're going to add a zero at a specific value. And let's say we're going to add this at location. We don't want to add it on top of one of our existing poles. So let's add it at, for example, minus 0.5. And so what that does is that creates a pull an extra 0 in here. And so if you need to zoom in ever, you can come over to the root locus editor and grab this zoom tool. But you can see this red circle is something that we just added, and so it changes the way the root locus looks. And so what this says is that there is a branch that reaches out here, but the other branch essentially starts at the pole at 0 and ends at this 0 right here. And that makes it still not possible to meet our time domain specifications. However, we could play around with this. So what's cool about this is that you can not only grab the pink dots, but you can also grab the 0. And so now what we're doing is we're effectively changing the derivative gain because we're grabbing the location of that 0 and moving it around. And now what you see is now we've moved the root locus to a point where there is a value where you can get these poles into a position that satisfy our time domain specs. And so then this, in this case, is no longer a simple second order system. So this is merely, again, going to be an approximation, but they're going to inform our design criteria and our design choices in a directionally correct way. And so that's the important thing, is to kind of understand the direction so that by, for example, moving these poles further to the down from the imaginary axis to the real axis, we're increasing damping, which should lead to less overshoot. And so you can kind of see that as if we move back here, you've got 11 overshoot. As you move further forward, now we're down to 8 overshoot, and so on. And so at the same time, we are also changing our rise time, and that's going to be based on the distance away from the origin. So anyway, so this is a brief intro into how to use the RL tool so that you can approach some of these design problems. So again, these give you exact information. This gives you directionally correct information based on a pure second order system. And your knowledge about how adding poles and zeros and other things into the root locus using the controller to add those terms is going to help you figure out how to change the shape of the root locus so that you can achieve these design specifications.